Let's talk about graph theory. So a graph is like a picture like this, right? This is a graph. It's got dots and lines. The dots are called the vertices. Each one is a vertex. The plural is vertices. The lines are called edges. And then another important piece of terminology is the degree of a vertex. Anybody remember, for example, what's the degree of this vertex? You remember what that means? It's a number. Show me the fingers or shout it out. I see some fingers. It's 3. This one, the degree is just how many edges hit the vertex. So this one right here is degree 3. This is a degree 1, that's a 2, and that's a 2, right? So it's easy to tell by looking at a vertex what the degree is. It's how many edges go into it. The degree is often interesting or useful for a specific example of a graph. That's a picture of a specific graph. I might, from time to time, encourage you to think about a graph that's maybe, like graphs which are useful in the real world tend to be too big to draw in a simple picture like this. But we could do something like imagine a graph, this is just to get us thinking here, where how about each full-time Fairfield University student is a vertex. So this has many, many vertices. I don't know how many. 5,000? How many? I don't know. Doesn't matter. A lot of vertices. And each one of you represents a vertex in this graph. And I have to tell you what the edges are. Let's say an edge connects any two who are in a class together, like right now, this semester. Right? So if you imagine this graph, it has many vertices in it, and like you represent one of them. And you actually, all of us in this room right now, I suppose I didn't include myself, but all of you in this room, in this graph will be connected by an edge because you're all in this class together. But you are also connected to other people who are in your other classes. Sorry. That makes a graph. Can we imagine, anybody want to estimate something like, what is your degree in this graph? Remember, the degree of a vertex would be how many edges are touching that vertex. Anybody have I mean, you probably don't know the answer exactly, but approximately? Yeah? 4 and 6? That's true. Yeah, so people, typically take like 5 classes. That's the usual, right? Remember, I'm asking you how many edges are there that connect to you. Now, you are already connected to all of these other people in this room, right? But also connected to everybody else in all of your other classes, right? So how many total connections would that be? I think it's more than 5 or 6, right? Because you're connected to everybody else in all your classes. Yeah. Yeah, maybe like 100. This would be, the question really boils down to how many total other students are you in the same class as? And there's a lot, right? All of these people, plus a whole bunch of other ones from all your other classes. So what's your degree in this graph? I mean, I don't know exactly, but you got 5 classes and let's say an average of 20 people in each of those classes. I would say about 100, right? This represents the total number of people in classes with you, which is probably about 100. Depends on what classes you're taking, I suppose. Total number of people in classes with you, right? How about this? Is the graph connected? Remember, connected means that it's sort of like all in one chunk. The more technical way of saying that is it's possible to get from any one vertex to any other one by following edges along a path. Is the graph connected? the question you have to ask yourself for this one is something like, if you just take another random student at the university, you're probably not in a class with them, but is it typically going to be true that you're in a class with somebody who's in a class with somebody who's in a class with somebody who eventually you get to them? I think probably that is true of all the students at the university. Unless there's like somebody who's only taking independent study classes or something, like you're gonna be able to get to everybody else. So is the graph connected? I will say probably yes. I don't know this for a fact, but probably if you choose any other student at the university, it is possible to sort of make a chain of, I know a guy who knows a guy who knows a guy kind of thing to get to the other student in terms of being in the same class as them. All right? These are basic questions you might want to answer about an imagined graph. How about this? I don't know if I said this. Each full-time Fairfield University student. What if we include? I suppose I never explicitly excluded them, but what if we include abroad students? All the Fairfield students who are currently somewhere else at a university in England or whatever. What difference does that make? I think actually in this case it becomes disconnected, right? Because those people who are like in England right now, they are not in a class with you, and also you can't even it's not like someone, you're in a class with someone who's in a class with someone who's in a class with someone who's in a class with them. That's not possible, right? Because they're in England. All the other people in their classes are in England. They aren't in the same class. So if we include abroad students, then it's disconnected. It will no longer be possible to make one of those sort of chains of students to get from here to there, right? All right, I got one more example like this, and then we'll move on to something else. I want us all to get used to thinking of kind of real-world scenarios as if they were graphs, and then answering questions about the graphs and making basic relationships between the real-world scenario and the graph. How about this one? This is another graph. How about another graph of Fairfield University students? And let's say this time you are all in the graph, but this time an edge, I have to tell you what makes an edge connect one to another. An edge connects any two students from the same U.S. state. Let's just assume for now that everybody at Fairfield University comes from a specific United State. I know that's not true, but let's just pretend like it is. All right? All the students at the university are individual vertices, and your vertex is connected to anybody else if you come from the same United State. All right? So, I would ask you sort of basic questions about this. How about Joe from Massachusetts versus, Sam from California, right? Imagine these two people. I'll ask you, who has, in this graph, who has the higher degree? That means, remember the degree is how many people you are connected to in the graph by an edge? What do you think?
I was going to say Joe.
Joe, yeah. Why is that?
Because everyone's from Mass. Well, most people are from Mass here, and a lot of people are from California.
Yeah, right. It's because at Fairfield University, there are more people from Massachusetts than there are from California. And so Joe's going to be connected to a lot of people. That is all the other people from Massachusetts. Whereas Sam will only be connected to a few people, whoever's from California. So the answer is Joe. Although you have to know something about the university to know this, but this is because there are lots more from Massachusetts than from California at our dear university, right? How about this? Is the graph connected? Remember, connected means, if you were to look at a picture, connected means it's all kind of in one chunk, but more more technically, it means you can get from any one vertex to another one by following a path of edges. Is this one going to be connected? I see some people saying no. Actually, I think if you think about it, like for example, can you get from Joe to Sam by following edges in the graph? Every edge coming out of Joe is to someone else from Massachusetts. I think if you're following edges and you start at Joe, you're never going to end up at Sam because you can't get there from here in this graph, right? If you're just following edges, the only place you can ever get starting at Joe is other people from Massachusetts because there is no edge that connects anyone from Massachusetts to California. So the answer here is no. In fact, you can say this graph will naturally fall into several clumps. There's going to be one chunk of people from Massachusetts. There's another chunk of people from Connecticut. Every state will have its own region of the graph. So each state, actually there's a term for that which I think I didn't say last time. Each state has its own component, is what these are called in the graph. This graph has like one big piece of all the people from Connecticut. It has another big piece of all the people from Massachusetts, etc. And there is no way to follow edges to get from one of these components to another. All right? Any thoughts about that? This is just sort of, can you imagine graphs and then say fairly straightforward things about them? All right. Graphs are useful in the real world. I mean, these are kind of made up examples and I'm not sure are terribly useful. But I hope you can imagine that graphs are useful. I'm just going to give you sort of a brief list of settings in which graphs, I will say, graphs arise naturally in the real world. For example, road maps and like GPS navigators. How does the lady know how to get from your house to your mom's house? Maybe your house is your mom's house. My house is different from my mom's house because I'm a grown man. How does the lady know how to get from here to there? Basically, my house is like a vertex on this graph, and the roads are edges connecting all the different locations. And the lady finds a path from one place to another by following good edges, where good means like there's not a lot of traffic or whatever. So road maps and navigations, you can imagine. Now this will be done, I don't know actually how they do this inside the computers, but vertices are either locations like specific destinations or maybe road intersections, right? Where two roads cross, they make kind of a nice little point there, which it makes sense to call that a vertex in a graph. And then let me just say, path finding is a big deal. So I hope it won't surprise you to know that there are people, there are mathematicians who it's like their whole thing in mathematics is methods for finding paths in graphs. This sounds like a very simple thing, but it's actually super important in lots of different applications. So that's why people care about it. All right, you got to find the best path. How about another one? How about airline routes? This is very similar. You've probably seen like maps of airline routes. They look something like, here's a map of the United States, and you got like all the different cities, and they have these like lines between them, right? This is what a map of airline routes looks like. What's interesting about these routes is like that line, when you see this line on a map, the plane doesn't really actually like literally follow that line. The line is just representative of the fact that there is a plane that goes from this city to that city. So this is an example where the graph is actually somewhat abstracted from the real world. When you see these lines on an airline graph, it doesn't mean the plane actually flies right on the red line like Indiana Jones. It means that there is a connection between those two cities, and most people don't actually care. Does the plane really go on the line? It doesn't matter. It's just there is a connection. All right. In a similar vein, computer networks are most appropriately analyzed in terms of graphs. All right. And this is another great example where a connection between two computers on a network Now, there probably is like a literal wire going from one place to another, but actually where the wire is doesn't matter. All that matters is the fact that there is a connection. All right. Computer networks are super important. Also, things like social networks can be analyzed in terms of graphs. For instance, you could think of Twitter, the social network, as you could view this in terms of graphs. Let's say each user is a vertex, and every time somebody follows somebody else, that is represented by an edge from one to the other. Now, this is an example of a graph where the edges are sort of one directional, because you can follow somebody on Twitter, but they might not follow you back. So there's like a one-way connection here. Anyway, each user is a vertex, and each follow is an edge, right? And you can analyze things like that. I could ask you something like, I have a Twitter account, although I hardly ever tweet anything. And because of this, I have like 10 followers. Be sure to follow me on Twitter if you don't want to see anything. I could ask a question like something like, is it possible to get from me to Obama by just following from me, someone I follow, and then someone they follow, and then someone they follow, eventually they follow. I don't follow Obama. Nothing personal. I just don't. But could you get from me to Obama? This is a question that you could answer by looking at the graph, right, and finding a path on the graph. So these things are appropriately analyzed by graphs. Let me just say, I'm trying to give you a very broad overview, but I will just say it this way. Graphs are super important, but mostly in social sciences, right? Rather than, say, physics. I think probably the way our math education for kids is geared, basically all the math that a kid learns is geared towards, first of all, just like ordinary adding and multiplying, but then also maybe more complicated stuff for the purpose of doing physical sciences. That's why you learn about continuous functions and all that kind of stuff. Graph theory doesn't appear so much in physics, but it is super useful in social sciences and kind of like analysis of like man-made structures or societal structures. Graph theory is super important. All right, we're about to start talking about something actually technical about this. All of this has been by means of sort of an introduction. I'm trying to convince you that graph theory is important for a great many things. It is important for a great many things. Let me tell you about just a little sort of history about this. The OG graph theory problem. In terms of the history of mathematics, certainly compared to the other stuff that you learn in, say, as a high school math student, which is all quite old, the original graph theory problem was done in the 1700s. This is called the 7 Bridges of Königsberg. This is a city in it was in Germany or Austria, something like that. Sorry, I don't know. The 7 bridges problem. Here's the situation. There's in this city. I'm drawing a picture of the city now. Maybe I'll go past the page break here. There's a river, and we have the north bank of the river and the south bank of the river, and there's 2 islands in the river, like this. All right, and the islands are connected to the land and to each other by bridges, and there are 7 bridges. There's one here, 1 here, 1 here, 2 here, and 2 here. All right, those are the bridges connecting the islands to the land. And this was apparently like a sort of a local folklore type of a thing. There was a question that people asked, and this somehow involved going something like a pub crawl on these islands. Can you walk from one place to another? But specifically about the bridges. can you walk across all 7 bridges without repeating any? And end up where you started? That's the question. Sorry. All right. Can you walk across all 7 bridges and end up where you started? And this was a common sort of thing that people would talk about, apparently, in this city. And the mathematics of the time, I'm talking about the 1700s, there really wasn't a good way to think about this problem mathematically. Because it seems like, when you describe this problem to somebody, it seems like a geometry problem, right? Because it involves these shapes and these lines or whatever. It's vaguely geometric, but it does not have the same character as an ordinary geometry problem in the sense that actually you can't analyze this problem in terms of, say, measuring distances or measuring angles, because actually the distances are totally irrelevant here, and the angles are also irrelevant, right? All that matters is the way in which these things are connected together, but it doesn't actually matter how long the bridges are, how far apart the islands are. None of that is relevant. So this, I will say, feels like a geometry problem. I will say, feels like geometry. But it really has nothing to do with geometry in the ordinary sense. It has nothing to do with distances or specific shapes. It doesn't matter that these islands are like, I drew them like oval shapes. What if they were actually rectangles? It doesn't matter. None of that matters. So feels like geometry, but you can't actually use geometric methods to analyze this problem. And this is sort of the birth of, we recognize this problem as the birth of graph theory. So this was originally solved by a mathematician named Euler. The name is Euler. It looks like Euler. Don't say Euler. I will publicly mock you if you say Euler. It's a German name. It's Euler, all right? This is confusing, I know. Perhaps you know one of the most famous Greek mathematicians, Euclid. You've got to keep it straight. Euler is German. It's pronounced Euler. Euclid is Greek. It's pronounced Euclid. I know it's confusing. Euler. Anyway, this was solved by Euler, and today Euler is recognized as the inventor of graph theory. It's not geometry, even though it looks like geometry, and it is somehow about shapes, but it has nothing to do with specific shapes. It's about things being connected up with one another. All right, and we're going to talk about this problem. Basically, the way that Euler analyzed this is this picture here. He realized, I'm going to copy this down here. Huh? I keep on saying the precise shapes and distances or whatever are irrelevant in this picture. All that matters is how the stuff is connected together. Euler realized that really this island, say over here, it doesn't matter what it looks like. You might as well just think of it as one thing on that island over there. You might as well think of the whole north bank of the river. Also, doesn't matter how long it is or what shape it is. You might as well just think of that as its own one thing. Same with the south side, and same with this one, right? Euler decided this problem, the picture there is misleading. The only thing that matters are these 4 locations and the ways in which they are connected. So Euler, his concept was to turn this whole thing into a graph. And the graph looks like this. It has 4 vertices, and it has an edge going across the middle, which is the bridge in the middle. It also has an edge like this, which corresponds to this connection from the south bank to the island on the right. It also has 2 edges over here, 2 edges over here, and 1 edge over here. All right. So Euler realized that this thing, which looks more complicated, actually is most appropriately viewed as this graph. And then he did some stuff with the graph. to show, to answer the question about the bridges. And we're actually going to come back to that. But this is the important, this is sort of the graph version of the 7 bridges. All right. That's the end of my little historical information. Let's talk about. Anybody got any questions about this? I think it's an interesting and extremely important area of mathematics today, which most kids don't learn anything about it, just because I don't know why. I'm not in charge in high schools. All right, let's talk a little bit technically about this. So I have said a graph is a thing like, it's got vertices. I'll draw another example graph, a thing like that, right? From a geometric point of view, this graph looks like a pentagon with an extra edge on it, right? This is a pretty sloppy looking graph. The edges are supposed to actually touch the vertices, and that looks like 2 vertices there. You know what I mean, right? It looks like a pentagon, but actually, similar to what I've been saying for the past few minutes, the precise arrangement here, the location of these points is not really relevant, and exactly where the lines go, how you draw the lines also is not relevant. Actually, that's the same as, like that first graph that I drew is the same as this. I'm trying to hit all the points. This is like I drew this one sort of like a lollipop, a circle with an extra line on it. Those are the same graph, right? They look slightly different because I drew the lines differently. Geometrically, of course, a pentagon is very different from a circle, but in the context of graph theory, there's no difference at all. But this suggests that you may ask yourself the question, and I would encourage you to ask the question, if these 2 graphs are the same, then what really is the graph? I said before, like a graph is a thing like this. But apparently this is the same as that. So when I'm talking about this as a graph, I'm not actually specifically talking about this pentagon. I'm talking about some kind of deeper, there's some like deeper nature of the graph which makes these 2 things the same. All right? So there is a true definition. What is the graph, really? This is kind of like a sort of a stoner question. Like, what is it really, man? Like deep down inside, what is it? Because I said, this is a graph, but those 2 graphs are the same thing, even though they don't look the same. So when I say they're the same, what I'm talking about is some kind of deeper underlying something is the same about them. What exactly is it that's the same about them? Well, I'm going to tell you, the true definition of a graph actually doesn't use pictures at all. And that's because when you draw the picture, you're talking about something that's a little too specific. The true graph is something deeper and less specific than that. So what is the graph really? It consists, so this is what I want to talk about is the true definition of a graph. It's not a picture. What really is it? Man, the true definition of a graph is it consists of a set of vertices and a set of edges. Now, how you want to draw it is up to you, because different drawings can represent the same graph. But what's important, the important ingredients are, what are the vertices? And I don't even care where you draw them, just what are they? And what are the edges which connect the vertices up with one another? So, for example, this graph here, if I were to express the true nature of this graph, what it is I'm gonna, in order to talk about this specifically, you have to give names to the vertices. So I'm gonna label them like this, A, B, C, D, E, F, all right? So this graph truly is, it consists of a set of vertices and a set of edges. The vertex set is, this is how we write a set in mathematics, A, B, C, D, E, F. It is just a list of what the vertices are inside those curly brackets. The curly brackets are what we use to indicate a set of things, all right? So the vertex set is those, and the edge set is also a set. And here I'm going to just list out what are all the edges. And I'm going to write each edge as a little pair. So I include A, B. That means there's an edge from A to B. There's also, and you just have to write them all down, there's also an edge from B to C. There's also an edge from C to D. There's an edge from D to E. And there's an edge from A to E. And there's an edge from E to F. And I think I wrote down all of them. All right? That's what the graph is. So this is the true definition of what this graph is. It's not the picture. The true nature of the graph is something deeper than the picture. It is just this, and there's no simpler way to say it. Now, does this mean from now on I'm always going to write graphs like this? No, actually, in almost all cases, we're just going to draw the picture. But I just want us all to know the picture is not actually what the graph truly is. The graph truly is this just random jumble of stuff. Yes?
Is there like a difference between color and
No. Sorry, that's confusing. Sometimes when I draw them,
oh, no, that's fine.
I like to linger and scribble them in. Sometimes I'm in a hurry and I don't fill them in. Yeah, that's not meant to be a distinction. Thank you for that. All right, so you can go two ways with this, right? I could draw you a picture of a graph, and you'll see this on the homework. This is always very easy to do if you know what you're doing. I could draw a picture of the graph and tell you, give me the formal description of what it is. Or I could go the other way around. I give you the formal description, you draw me the picture. Let's just try one like that. How about draw the graph? Which has the vertex set. How about A, B, C, D, and the edge set AC, BC, AD, CC, and BD. All right, you got to get all the parentheses lined up properly in the edge set, because these things are meant to be, 2 by 2, and edge always goes from one vertex to another vertex, or maybe back to itself. All right, can we draw the graph? Maybe I'll give you a moment, see if you can do it. This is, like I said, not really hard. Just position the vertices wherever you like, and then draw in the appropriate edges. I'll do it slowly. Anybody get anything here? Here's how I'm going to do it. I would start by just drawing the vertices wherever you like. I put A, B, C, D kind of going clockwise around, although it doesn't matter how you arrange them. And then I'm going to connect up the edges. So there's an edge from A to C, so that's a line like that. There's an edge from B to C, that's like that. There's an edge from A to D, which is like that. There's an edge from C to C, which is a looping edge like that. And there's an edge from B to D, which is like that. This is the graph. I hope yours looks something like that. Although actually, yours could look quite different if you decided to arrange the vertices differently. So it could look like that, or what if, I don't know if anybody did this, but if I wrote A, C, B, D like this, in that case the graph looks like I have an edge from A to C, I have an edge from B to C, an edge from A to D, an edge from C to itself, and an edge from B to D. All right? Now it looks like that. Those are actually the same graph, even though they look, they are drawn differently. It is the same graph. These are the same graph, drawn differently. All right. The true nature of the graph is just what are the vertices and where are the edges. That's all that matters. So there are, it's definitely possible to draw the same graph in two different ways. All right. Yeah.
I think we talked about this, but when C has its goes back to itself, how many degrees is that?
Yeah, that counts. You count each individual end here counts separately. So this will be degree 4. Yeah. Yeah, that usually doesn't come up, but actually it is important sometimes to keep it in mind. All right. Excellent. We got 13 minutes remaining. I think we can talk a little bit about this bridges problem then. So, like I said, this is the formal description of a graph. We are usually not going to talk about a graph in this way. Usually we'll just draw the picture and that'll be it. But I just want everyone to keep in mind, the picture is not really what the graph is. Let's talk about the 7 bridges problem in its version as a graph. That original picture that I drew is totally irrelevant for answering the question about the bridges. Remember, the question was, is it possible to walk across each bridge and end up back where you started without repeating any bridges? So translated in terms of a graph theory question, this is the 7 bridges problem again. The bridges of Königsberg. As a graph, what is this about? Well, as a graph, this is about, is there a path? Remember, each of those edges represents one of the bridges, right? And there are 7 of them. As a graph theory problem, this is about, is there a path which starts somewhere, goes across every edge once, and then ends up back where it started? We had a word, actually, last time for a path which ends in the same place where it started. Anybody happen to remember this? It was in my original list of vocabulary. It's called a circuit. So a circuit is a path which begins and ends in the same place. So as a graph, this question is there a circuit? Circuit, that means a path which starts and ends in the same place. Is there a circuit which uses every edge exactly once? I mean, you have to use every edge once, and you can't use any more than once, right? That's actually the question of the bridges problem. Can you walk across every edge? Can you walk across every bridge without repeating any? It means, is there a circuit in the graph which uses every edge exactly once? Anybody just look at this? Can you see how to do that? Or maybe it's not possible. Actually, the reason why this problem existed for so long, or that people liked to talk about this problem for so long, is that it turns out not to be possible. Although the hard thing about the problem is to actually explain in simple terms exactly why is it not possible. But you can try to just play around with it. You could say, what if I started over here? Let's say I started here. I could try to do it. Go over maybe like this, maybe like that, over here. Actually, now I'm stuck because I can't reuse any bridges. So that didn't work. Maybe I could try instead like this. I don't know, I just got stuck again. Right? The best you can do without some kind of deeper knowledge, the best you can do just try it out a bunch of times and say, well, that didn't work. But that doesn't constitute an explanation of why it's impossible. All right? So Euler's big achievement was Euler demonstrated that actually this is not possible. Now the bridges, this sort of 7 bridges is kind of a cute example and not terribly important in its own right. Like, it didn't really matter whether this was possible to do or not. But there are other situations in which the same question is actually important. And it's such an important concept that there's a word for it, or there's a name for it. I'll write this as a little definition. A circuit which uses every edge exactly once. That's what we're talking about here. A circuit which uses every edge. There's a special name for it. A circuit which uses every edge exactly once is called an Euler circuit. An Euler circuit. All right. These are, of course, named after Euler because he's the first person to ever, like, really seriously analyze this kind of a problem. Euler circuits are important in other contexts. So here's another example where you might want to think about an Euler circuit. Let's say this is a grid of streets and intersections, and right here, the one in the middle, the intersection in the middle, is where Mr. Plow lives. And let's say it snows and Mr. Plow wants to plow all the streets. Obviously, Mr. Plow does not want to revisit the same street twice. You want to just plow down each one, right? Can Mr. Plow visit each street once and then come home? This is the same question, right? Now I know in real life a real plow has to go every street twice, maybe once in each direction or something, but anyway, let's just think about these are very narrow streets which Mr. Plow can do all at once. All right? Can Mr. Plow visit each street once and then come home? It's really the same question. I mean, it's a totally different graph here. And is it possible here? Actually, there is a fairly straightforward method to tell if this is going to be possible or not. Because I know these fairly straightforward method, I can tell you actually it's not possible in this picture either. So this one is also impossible. You'd have to think about, okay, can I start here and then cover each one without retracing any of them? I don't think so, right? It's not easy to do. Anyway, the answer, I will just say parenthetically, is no. Euler figured out a very easy way to decide the answer to a question like this in any graph that you can imagine. Let's just I want to look at a simple example. I think we don't have time to, I'm going to tell you how to figure this out in all cases, but I don't think we quite have time. Here's another more interesting example, perhaps. This is a graph which has a vertex in the middle and also at all these corners and some extra edges on the two sides like that. So I'm going to call these A, B, C in the middle, D, and E. Does it have an Euler circuit? Actually, this one does. Can I give you a moment? See if you can find it. So, I don't care where you start. Let's just, for the sake of all getting the same answer, let's say you want to start at A. All right? You have to start at A, use every edge, and make it back to A. Actually, you're not all going to get the same answer. There are many ways that you could do this, but start at A, use every edge, don't duplicate any edges, and end up back at A. And the way we can write our answer is just, I'll start with A. Maybe if I wanted to say go to B first, I would just write A, then B, then whatever else, blah, 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 blah. And eventually you should end up back at A, right? That's the idea. So this is how I would expect you to write your answer. See if you can make it happen sort of in your head or maybe by scribbling on your picture. And then list out the vertices in order that you went to. I'll give you a moment, and then we can chat about it. perhaps you're wondering, can I revisit the same vertex more than once? Yes, you can. Actually, you're going to have to, but you just can't use the same edge more than once. Can we talk about it? We got to leave in a moment. Anyone want to? Can you tell me what your path was? Yeah.
You go A to B. Then you go down to E.
All right.
Back to B. You do C, D. Back to E. C, A, D, A.
Okay. You probably didn't write exactly the same thing, but let me just see if I agree with this. So from A, I go to B. This is how I would write this answer. From A to B, and then to E, which is down here, and then to C, which is in the middle, and then to D, which is down here.
You go back to
Did I miss
E
something?
from E.
Oh, A, B, E, B. All right. I messed it up already. Like that. And then down to C. Thank you for that. And then to D, and then to E, and then to C again. I like this. Then to A, and then D, and then back to A. And I think that does it, right? Excellent. Like I said, there are many other ways that you could have done this, but this is one possible answer. So I suppose the answer here is yes. All right. We'll talk next time about how you can tell. Actually, it's very easy to tell if you know what to look for.